Welcome, my friends! I'm so excited because we get to talk about the central limit theorem in this video, which is the most important theorem in statistics and is core to much of the hypothesis tests and confidence intervals that we're going to do in future videos. So let's go ahead and get started. Alright, before we can talk about the central limit theorem, we have to make sure that we are familiar with a couple of different terms and symbols that we have used in previous sections. So first of all, do you remember what is meant by a statistic? Well, a statistic is a single number that somehow describes your sample. And do you know how that differs from a parameter? Well, a parameter is the same thing. It's still a single number that somehow describes something, but now it's not going to be the sample. It's going to be your entire population. And we use different symbols to represent different things that we calculate based on if we have a statistic, based on a sample, or a parameter, based on a population. For example, if we have the mean, a measure of the center of our data set, if it is based on a sample, then we use the symbol x bar. X bar is the sample mean, which is a statistic. On the other hand, if we have the mean based on the entire population that you are interested in studying, then we would use the symbol of mu. On the other hand, if you have the standard deviation, which is a measure of how spread out the values are in your distribution, then we would use the lowercase letter s. And if you have the population standard deviation, then we would use the Greek letter sigma. We also have the proportion, which is sometimes thought of as like a proportion out of a total or maybe a percentage out of a total. And we would use p hat if it's based on a sample, and just plain old p if it is based on a population. So hopefully you have the difference between these symbols down by now. If not, then I strongly encourage you to spend some time focusing on these and seeing if you can memorize these, because at this stage in the class we kind of expect you to know the difference between a lot of these symbols, especially between x bar and mu. So at the very least, make sure at this point you understand that x bar is the sample mean and mu is the population mean. Now, instead of just giving you the definition of the central limit theorem, I'm going to try to build up to it by looking at an example. So here's the example. Suppose that the population mean age of all residents of Grand Rapids is mu equals 32. So notice I'm using mu here for the population mean. This is the mean based on every single resident of Grand Rapids. Further, suppose that you personally do not know what the population mean age of a Grand Rapids resident is, and you're interested in estimating the value. So that's typically going to be the case. You're not usually going to know the value of a population mean because typically the population has thousands or maybe millions of individuals. So you probably won't know this value exactly. And we're saying here, we're going to try to estimate this value. The true number is 32, and we're going to go ahead and try to estimate that maybe with a sample. So you, as well as all the other students in your statistics class, are set up with the task of estimating the mean age using a sample. Let's assume that everyone in your class uses a random sample of size n equals 64. So each student finds 64 random Grand Rapids residents and asks them their age, and then finds the average or mean based on those 64 individuals. Because each student is only finding the sample mean, x bar, they're likely going to get a different result, either a little bit higher or lower than that true mean of mu equals 32. So let's say student number 1 goes out there and finds his 64 individuals, adds up all the ages and divides by 64, and they end up getting a value a little bit greater than 32. They get x bar of 33, a sample mean of 33. And student number 2 does the same process. They get 64 different random people, and they find the mean to be 30. Student 3 gets 32, student 4 gets 31, student 5 gets 29, student 6 gets 37, etc. for all of the different students. Now, it's not unsurprising that each student got a different sample mean. That's to be expected. We know the true population mean is 32, but when you actually go out and take a sample, you're probably going to get a value that's a little bit higher or lower than 32, which is exactly what we see here. All of these different possible sample means make up what is called the sampling distribution, which is a very important term as it relates to the central limit theorem. Most of the means in the sampling distribution are going to be just a little bit higher or a little bit lower than the true population mean of 32. But all of these sample means should average to a value that's very close to the true population mean of 32. And I have done that in this case. So if you were to add up all of these means, 33 plus 30 plus 32 plus 31 plus 29 and 37, and you divide all of those by 6, they do turn out to be 32 exactly. Now, is that always going to happen? Not necessarily, but if you had a very, very large number of sample means, you would expect that the mean of all of those sample means would be equal to 32 or very, very close to that value of 32. Now, the central limit theorem, which is the focus of this chapter, states that the values in a sampling distribution, meaning each of these sample means, right? Each of those sample means will follow a normal distribution as long as at least one of the following conditions are true. So there are two possible conditions, and we only have to meet one out of these two conditions. The first condition is that the initial distribution sampled from must be normal. In our example, the age of individuals in Grand Rapids. That means if you got a whole bunch of people from Grand Rapids together and found all of their ages and made a histogram out of those ages, if it followed a normal distribution, then you could say that the central limit theorem applies. And the sampling distribution, plotting all these sample means, you can expect those to be normal as well. Condition 2 is the sample size used to compute each of those sample means must be at least 30, or n is greater than or equal to 30. So in our example, we were using a sample size of 64 to calculate each of these sample means. So what this is really saying is even if we didn't meet that first condition, as long as we have a sample size of at least 30, if we were to plot these sample means and make a histogram out of these sample means, we would expect that to be a normal distribution as long as the sample size is at least 30, which is kind of a remarkable fact. Let's think about the central limit theorem in the context of a different example, which is rolling a fair six-sided die. So on a fair six-sided die, there are 6 different sides, and each of them are equally likely. So if you're going to roll a single die, you're going to have an equal chance to roll any number from 1 through 6. And that's going to create what we call a uniform distribution, an equal chance to roll any of those 6 numbers. So this would be an example where we have not met the first condition. The initial distribution which we are sampling from, which is a roll of the die, is not a normal distribution. This is a uniform distribution. So that means the only way for the central limit theorem to apply in this example would be to meet the second condition. So that means we must have a sample size at least 30. So let's say that we have a sample size of 100. Really what that would mean is you have a whole bunch of people who have gotten together and each of them are going to roll 100 dice. And they're going to find the average of those 100 dice. And we're going to make a histogram of all of those averages or all of those means. Well, based on the central limit theorem, those values in that sampling distribution, since we're plotting sample means, are going to follow a normal distribution not because we met the first condition, but because we met the second condition. We only have to meet one out of these two conditions. Since we're using a sample size that is at least 30, we can state that we're going to have a normal distribution for the mean of those dice rolls. When referring to a sampling distribution, we are going to use a subscript of x bar. So for example, we may have mu with a subscript x bar, which would be the mean of the sampling distribution, and sigma with a subscript x bar, which would be the standard deviation of a sampling distribution. So here is a statement that mu of x bar, or the mean of the sampling distribution, is equal to mu. So what does this mean? The above statement means that the mean of sample means should be the same as the population mean, which is actually a statement that I made earlier. If each student found the mean age, x bar, then the mean of all of those means should be the same as the population mean or very close to it. I think an easier way to explain this is just to go back to this slide. Basically, all this is saying is if a whole bunch of individuals found a sample mean and we found the mean of all of those sample means, we would expect that to be 32 or very close to 32. That's really all this is saying. And then we have one more statement here, which is that the standard deviation of the sample mean, or the standard deviation of our sampling distribution, is equal to, well, whatever the standard deviation was of the distribution you drew from, divided by the square root of the sample size that you used to calculate that sample mean. So what does this mean? This means that, on average, the sample mean is going to differ from the population mean by about sigma over the square root of n, where sigma is the standard deviation of that initial variable that you were drawing from, and then n is the sample size used to calculate each mean. This quantity is what we call the standard error. So once again, we may want to kind of look back at this example to understand that a little bit better. The standard error, or sigma of x bar, is really just saying, on average, how far does each of these sample means differ from the population mean? The population mean is 32, and these values are a little bit above or a little bit below 32 on average. On average, how far away are each of these values from 32? That's what we call the standard error, which is sigma of x bar, or sigma over the square root of n. Okay, let's apply some of these concepts more directly to the example we looked at earlier. So suppose that the population mean age of all residents of Grand Rapids is mu equals 32, with a standard deviation of sigma equals 6. You don't know what the population mean is, so you decide to take a sample mean from a sample of size n equals 64. Everyone else in your statistics class does the same thing. Once everyone reports their sample means, you decide to find the mean of all the sample means. Approximately what number can you expect to get? Pause the video and think about this question for a second before going on to see the answer. Well, this question is simply asking for the mean of the sampling distribution, or mu of x bar. Recall that mu of x bar is just equal to mu, so you should expect to get about 32 as your answer. The real population mean is 32, and if a whole bunch of people found sample means, you would expect that the mean of those sample means would be very close to the true population mean of 32. Here's another question. On average, how far away from the population mean of mu equals 32 can you expect each student's sample mean to be? Well, this question is just asking for sigma of x bar, or the standard error. The standard error tells us on average how far away a sample mean would be from the population mean. We said on the previous slide we can calculate this value by taking the standard deviation of our initial variable, which we know to be 6, and dividing by the square root of our sample size, which we know to be 64. We can take 6 divided by the square root of 64, which is equal to 0.75. That means that each sample mean is going to be about 0.75 away from the true population mean of 32 on average. All right, we have one last question. If a histogram were to be made of all students' sample means, what shape would it follow? Well, of course, the answer is going to be normal based on the central limit theorem. We have to have met at least one of two conditions. Either the initial distribution had to follow a normal distribution, which we aren't really told, or we have to have a sample size of at least 30. In this case, our sample size is at least 30. We have a sample size of 64, so we are able to state that we have a normal distribution for our sample means. More specifically, we can say that the sample mean follows a normal distribution with a mean of 32 and a standard deviation of 0.75. All right, here's a problem for you to try. Suppose the population mean income of all working Grand Rapids individuals is mu equals $50,000, with a standard deviation of sigma equals $15,000. You personally don't know what the population mean is, so you decide to take a sample mean from a sample size of 36. A group of your friends decides to do the same. Once everyone reports their sample means, you decide to find the mean of all the sample means. Approximately what number can you expect to get? This first question is asking for mu of x bar, so if you're stuck on this one, look back to the previous slide to help you out. On average, how far away from the population mean of mu equals $50,000 can you expect each of your friends' sample means to be? This is asking for the standard deviation of x bar, or the standard error, which you can find by taking the standard deviation of 15,000 and dividing by the square root of 36, the sample size. Finally, if a histogram were to be made of all the sample means, what shape would it follow? So I'm not going to go over the answers to these questions because it literally is the exact same thing as the slide before. So if you are stuck, look back at this slide and that should be able to help you out. But I do strongly encourage you to pause the video and work through each of these problems. All right, now we're going to transition into the main bigger problems that are going to be associated with this section. So first, I want to remind you of what we called a problem type number 1 that we covered in the last section. So problem type 1 was when you were trying to find a probability related to a word problem on a normal distribution. So you were taking a value for x and somehow translating that into a probability. For example, what's the chance that I choose a random student and they score maybe higher than a 90% on a test if the test scores followed a normal distribution? Now, you might remember the steps that we use to complete one of these types of problems. First, you're going to want to write out a probability statement in terms of the variable. So that would be something like this. Maybe the chance that your variable is greater than something, maybe less than something, or in the second case, we have maybe between two different values. And then the next step would be to convert the value of x, or the values, if there are two, into a z-score using the z-score formula. And then you can write a new probability statement in terms of z rather than x based on the values you got from step number 2. So that would be something like, maybe you plug 35 into the formula, maybe you got 2 out. So then you would have the new statement in terms of z with z greater than 2 rather than x greater than 35. Or maybe you got -1 and 3 when you plugged in these values into the formula. So then this would be your new probability statement, basically just kind of changed units. And then you can find the answer by using the normal CDF function on the TI-84 calculator. And you may also want to draw a picture of the normal distribution to help you. Now, the reason why I'm kind of revisiting this right here is because the new problem that we're going to solve now related to the central limit theorem is going to be very, very close to this one. There's just going to be one small change that's going to make it different. So this is what I'm going to call a problem type number 3, which is instead of going from x to probability, now we're going from x bar to probability. So the difference is, x just says one single value or one single individual. That would be like saying, what's the chance that one single student's test score is greater than a 90%, right? Whereas x bar would be saying something like, what's the chance that I take a sample of, 50 students or 30 students, and what's the chance that the mean from that sample is greater than 90 or less than 90 or something along those lines, right? So now we're dealing with probabilities related to a sample rather than just one single individual. And we'll see problems here, exactly what that's going to look like in just a second. But here are the steps that you're going to use for the problem type number 3. Now, the first step is what we've already kind of been doing here in the last several slides here. We're going to basically describe the distribution of our sample mean. So this is kind of where the central limit theorem applies. Remember, we said that our sample mean is going to follow a normal distribution as long as we had met one out of those two conditions, or at least one of those two conditions. We have to either have a normal distribution for our variable or a sample size of at least 30. And as long as that is the case, which is going to be the case for any of these problems that we do, we can say our sample mean follows a normal distribution that has the mean that's the same as the mean of the population and a standard deviation which is equal to the standard error term, sigma over the square root of n. And all the remaining steps are basically just a repeat of the problem type number 1. So now you're going to write a probability statement, but in terms of x bar, because they would be asking you a probability related to x bar, right? So that's going to look something like this. Maybe the chance that x bar is greater than 35, or maybe between two different values. But the main difference here is you got to make sure you remember to use x bar, because they will be asking about a probability related to a mean. So make sure you have the bar on your x's here. And then you're going to find a z-score using a very, very slightly modified z-score formula. Really, in general, you can always find a z-score by taking a value and subtracting the mean of that value and then dividing by the standard deviation. And you're really doing the same thing here, but now it's just applied to x bar. You take x bar and you take like the mean of x bar, which is really just going to be sigma of x bar. I've taken off the x bar here because it's the same as just the mean. And then you're dividing by the standard error, which is sigma of x bar. So really a very similar formula to what we've seen before, but now it's specifically applying to x bar. And then you're going to write a new probability statement in terms of the z-score that you got when you plugged in here. So maybe you plugged 35 in and you got 2 out, so then you would use that. Or maybe you plugged 57 and 73 and you got -1 and 3 out when you use this formula. And then the last step would be to just find the probability using normal CDF. All right, so let's go ahead and look at a problem. Here's the same example that we had before, where the mean age of all Grand Rapids residents is 32 with a standard deviation of 6. We don't personally know what the mean is, so we're going to take a sample of size 64, right? So we're assuming it's 32 for the purposes of the problem, but you as the person taking a sample don't really know that number. So here is kind of the question here. We know that if you take a sample mean, it's probably not going to match that population mean exactly. Kind of going to probably be a little bit higher, a little bit lower. And the question they're asking is, what is the probability that the mean that you take from your sample is greater than 33? I should also mention here, it does really have to be a random sample, kind of equal chance to choose anyone from the population. So this is what we call a problem type number 3. Hopefully you kind of recognize. They're asking for a probability with relation to the mean or the sample mean, right? So we know that it's going to be the problem type 3, and we're going to be following the steps related to that. right? So the steps are going to be, well, first we need to write out the kind of the distribution of x bar. We've already done this in a previous step here, right? The mean is going to follow a normal distribution because we have met the second condition here of a sample size of at least 30. It's going to have the same mean as the population that they stated, and the standard error or standard deviation of x bar is going to be whatever they gave us divided by the square root of our sample size of 64. And if you divide that out, you're going to get 0.75. Then from there, we can go to step number 2, which is to write out our probability statement. So our probability statement is going to be based on this sentence right here. What is the probability that the mean from your sample, x bar, is greater than 33? So that's what we have right here, the chance that x bar is greater than 33. At this stage, you can go ahead and you can draw the distribution if you'd like to. The mean of 32 is going to be right down the middle, and the 33 that we are asking about is going to be somewhere to the right, and we want the probability that we are greater than 33. So step number 3 is going to be to find the z-score related to this, which is basically just going to be plugging into this formula here. We'll take the x bar of 33, subtract the mean of 32, and divide by sigma of x bar, which is 0.75. If you go ahead and do that, you're going to get approximately 1.33, or it's really 1.33 repeating. So at that stage, you can go ahead and put the z-score on your distribution. So 1.33 is going to kind of correspond to that 33 that we had right there. And now we're basically just finding the probability that z is greater than 1.33. So these are equivalent probability statements. The chance that x bar is greater than 33 is going to be the same thing as the chance that z is greater than 1.3 repeating. We've kind of just changed units from x bar to z-scores. And then finally, we can use our normal CDF function on the calculator to find the probability. So just as a reminder, we can find that by going to second and distribution on our calculator and choosing the second option down. The lower bound is going to be in terms of z-scores. It's going to be where the shaded region starts, which in this case is 1.33. And then the upper bound is going to be where the shaded region ends. In this case, there really is no ending point. We just put in a really big number, which typically I just use 1,000. And then we're going to always leave mu and sigma as 0 and 1 to tell the calculator we're putting in z-scores, because the z distribution has a mean of 0 and standard deviation of 1. We can go ahead and paste, and we're going to get our answer, which is 0.0918, it looks like. So that is that probability in the tail there, or the chance that the mean from your sample is greater than 33. We know that on average, our mean is probably going to be pretty close to 32. But if we take a sample mean, there is a chance that is greater than 33, and there's about a 9% chance of that happening. All right, let's go ahead and try one more example. So we have the same exact information up here, but the difference here is going to be the question. Now they're going to ask about what's the probability that the mean from our sample is between 30 and 32.5. Right, so we know that our sample mean should be pretty close to the population mean of 32, but it could be a little bit higher or lower. What's the chance that it's between 30 and 32.5? So once again, you should recognize that it's a probability related to the sample mean. So we're going to be using the problem type 3 kind of steps here. We're going from a sample mean to a probability. So the very first step is to write out the distribution of our sample mean, which we've already done in previous parts. So I'm just basically copying that over here. Step number 2 is to be basically to write out our probability statement. Now, you may remember that when we have two different numbers in our probability, we kind of write it in this way. We're going to have the lower number first, which is 30, and we're going to have the higher number second, which is 32.5. We have our variable in the middle, which is x bar, and then we have that's kind of surrounded by less than sign. So altogether, this is saying our sample mean is less than 32.5, but at the same time, it is greater than 30. So on the picture, it's going to look something like this. 32 is in the middle, so we kind of cross over the middle here. We have 30 on the left-hand side, and then 32.5 is a little bit to the right of the population mean of 32. Then we can go ahead and we can find the z-score using the z-score formula, but since we have two different values in our probability statement, we're going to actually have to find two separate z-scores. So the first z-score is going to be related to that 30 value, so we can take 30 and subtract the mean of 32. And divide by the standard deviation of x bar, which was found right here, of 0.75. And if you type that into your calculator, you should get negative 2.67. And we can do the exact same thing with the second z-score. So the second z-score is going to relate to 32.5. We can subtract the mean of 32 and then divide by the standard deviation of 0.75, and we will get 0.67 approximately. So we can go ahead and put those numbers on our distribution on a second axis related to z-scores. And we can go ahead and write out our new probability statement, this time in terms of z. So instead of x bar in the middle, now we have z in the middle, and we have those two z-scores that we just calculated in step number 3. Finally, we can go ahead and we can go and plug these into normal CDF on our TI-84 calculator. So we can go to second distribution and option number 2. We can put in the lower bound, which is the lower bound z-score. Make sure you're putting in z-scores here of negative 2.67. And then the upper bound of 0.67. That's where the shaded region ends. Leave mu and sigma at 0 and 1. Go ahead and paste, and we'll get the answer here, which looks like it is 0.7448, because that 7 will round this up to an 8. And that represents the area on the distribution between either 30 and 32.5, or between a z-score of negative 2.67 and positive 0.67. Altogether, this really means there's about a 74, 75%-ish chance that if you take a sample mean, that is somewhere between 30 and 32.5. All right, so here is a problem for you to try. Suppose the mean number of steps an American takes in a day is 4,000 steps with a standard deviation of 1,400. You, as the researcher, don't actually know this information or know this number. You don't know what the mean number of steps is for an American, but you're going to go ahead and try to estimate it by taking a sample. You go ahead and you take a sample of 49 Americans, and they were randomly selected, and you're asked about the number of steps that those people take in a day. So I'm going to ask you a number of different parts here, which are basically going to be very similar here, calculating some probabilities related to this distribution. So number 1, go ahead and write out the distribution of the sample mean. It's going to be normal, and then you have to basically find the mean and the standard deviation and put those in parentheses like we've done previously. And then I have 2 different probability questions for you. So go ahead and pause the video and try these out. And then in just a minute, I'm going to go ahead and go through parts 1 and 2. All right, so hopefully you've given that a try. I'm going to go ahead and go through parts 1 and 2. So writing out the distribution of the sample mean, it's going to be normal because we have a sample size of at least 49. We haven't met it with that first condition, right? We don't really know what the distribution is. They don't say anything about the distribution of the steps. But we do know that the sample mean is going to follow a normal distribution because our sample size is at least 30. The mean is going to be 4,000. It's always the same as the mean that was given here. And then the standard deviation, or what we call the standard error, can be found by taking that standard deviation and dividing by the square root of 49. Really, the way you can view this, the 200 that we get is, on average, if you take a sample mean of sample size 49, you could expect to get a number pretty close to 4,000, but it wouldn't be that surprising for the number to differ by about 200 from that. So like maybe up to 4,200 or 3,800. On average, the sample means would differ from 4,000 by about 200 steps. The second question asks us, what's the probability that your sample mean is less than 3,650? So this is kind of like step 1 of a problem type number 3. And now we're going to be on step 2 for this part right here. So we're trying to find the chance that our sample mean is less than 3,650. So we could go ahead and draw that out on our distribution. It's going to look something like this. 4,000 is going to be in the middle. 3,650 is going to be somewhere to the left, and we're shading the area to the left of that. We can go ahead and find our z-score using the z-score formula, and that's going to give us negative 1.75 if we plug all those numbers in the appropriate places in the formula. 200 coming from here, 4,000 coming from here. And we could put those z-scores onto the distribution here. So 0 is in the middle, and negative 1.75 kind of corresponds to that 3,650. And finally, we can write a new probability statement for z less than negative 1.75, and then use normal CDF to find the answer. So the lower bound for normal CDF is going to be negative 1,000, because we have a less than. There is no lower bound of our shaded region. The upper bound of our shaded region, where it ends in terms of z-scores, is negative 1.75, so that's our upper bound. And then we're always going to put 0 and 1 as the mean and standard deviation of the z distribution. So that gives us about 0.0401. The chance that we take a sample mean, and for it to be less than 3,650 steps for those 49 students on average, that would be pretty unlikely. There would only be about a 4% chance of that happening, assuming that the true mean was 4,000. All right, so hopefully you've also tried number 3, or if not, you may want to try that now after you've seen how I did number 2. But this is going to be very similar to number 2, and also similar to the one that was done earlier in the video, so you can go back and kind of check that one out if you're still stuck on number 3. All right, that finishes everything I wanted to talk about in this video, so hopefully you found it useful, and I will see you in the next one.